So the next subject we're going to cover is also in theory. It also in theory has a lot to do with interparticle attractions. Okay, and this is how adding solute to solvent changes freezing temperatures and boiling temperatures. Okay, adding solute to solvent changes freezing temperatures and boiling temperatures. Okay, so this can be predicted mathematically. All right, and that's what we're going to be doing. So a couple of equations you need to know. One is, well, this is a general equation that applies to everything in chemistry. When I have a change in something, we define mathematically a change in something as being final minus initial. So if we're going to look at the change in temperature of something, we're going to talk about the change from the final temperature minus the initial temperature. Okay? Got it? That's the way we define change in almost everything we do in science. If we're mathematically defining change, it's some final minus initial. Okay? And since we're talking about temperature here, this is going to be final minus initial temperature. So we could have a change in freezing temperature that is temperature final minus temperature initial. And we could have a change in boiling temperature. I should make that lowercase f, I guess, here. That is temperature final minus temperature initial. So you see we got three different equations here. Does that make sense? Yeah, boiling, freezing. All right? All right. So this is the general equation, and we wrote this out specifically for freezing and specifically for boiling. Okay? All right. If we're looking at the freezing temperature, the change in freezing temperature, there is another equation that defines what happens when you put a solute in the solvent. There's another equation that defines the change in temperature as solute is increasingly added to the solvent. And that equation is this. We have I. Okay, in chemistry, I stands for something called the Hoff Factor. I'll talk about that in a minute. Times a constant that, by and large, we look up. We could calculate a constant, but there's a lot of constants already calculated for us. And in fact, you've got one of these on your test references. I'll show you in a minute. So, I'm sorry, this should be F because I'm talking about freezing, not boiling. I'm sorry. You can borrow some whiteout. You going to bring it back to me? Even the parts you put on your paper, you going to bring it back to me? No, you won't. You're lying. If you borrow my whiteout, you mean you're going to borrow the bottle, then you're going to use my whiteout. You're not bringing back the stuff you put on the paper.
Borrow the bottle?
Yeah. Okay? And this is the molar concentration. There you go. All right. So, this is our change in freezing temperature. Freezing temperature. Okay? This is called the Vant, lowercase v, capital F, factor, lowercase v, capital F, Vant Hoff factor. It's named for somebody, so we try to do their name, spell their name, and write their name the way they do it. Okay? This is a freezing point constant, or freezing temperature constant. And this is molal concentration. Okay? Now, the Vant Hoff factor. The Vant Hoff factor is more complex than we assume it to be in high school chemistry. We're simplifying here as we do a lot of things in high school chemistry. Simplifying almost to the point of absurdity. You've heard that phrase a lot in here. Okay? The Van Hoff factor is a combination of different things. But for high school chemistry, we simplify the Van Hoff factor to this. It is the number of particles that a formula unit of a compound breaks into. It's the number of particles that a formula unit of a compound breaks into. The number of particles that a formula unit of a compound breaks into. So here's a simple example. Sodium chloride. Sodium chloride in solid form. We're going to dissolve it. Let's say we dissolve it in water. How many particles does it break into?
Number of particles that a formula
unit breaks into. Okay, so what particles does sodium chloride break into when you dissolve it in water? Na plus and chloride ions. Okay, and how many particles is that? 2. So the Van Hoff factor then for sodium chloride in high school chemistry, we're going to say is 2. Okay? You with me? All right. How many particles? So in order to get separate particles, going back to Unit 5, actually Unit 4 when we started, okay, we said only 2 kinds of things break up. This is when we first encountered this when we're talking about net and complete ionic equations. What kind of chemicals break into separate particles? What kind of particles do we break up into separate ions?
Ionic.
This is the ionic equations. But what kind of substances do this? Aqueous acids and also something else. Aqueous acids and not bases, but it's bases fit into our category of the second thing. Ionic compounds. So aqueous acids and aqueous ionic compounds. Those are the only ones that have a Van Hoff factor greater than 1, because those are the only ones that break up into particles. Okay? Only aqueous ionic compounds, also known as aqueous salts, only aqueous salts and aqueous acids break up into multiple particles from the formula unit. Okay? So, is sugar ionic? Oh, come on. Really? Sugar's not ionic. Yeah, it's a covalent compound. What's the Van Hoff factor for sugar? 1. It doesn't break up. It's just 1. How about ammonia? Is ammonia ionic? If we dissolve ammonia in water, what's the Van Hoff factor? 1. It's not ionic or acidic. Yeah. Yes. Al, aluminum sulfate is what we're talking about. Al has a 3+ charge. Sulfate has a 2 negative charge, and you're correct on your answer. Here's one. How many sulfates do I need?
You need 2 aluminums and
2 aluminums,
and
3 sulfates to make aluminum sulfate, Al2, SO4, 3. How many particles do I have?
5.
5. 2 and 3 makes 5. So I, for aluminum sulfate, is going to be 5. Okay? That makes sense? That's how you figure it out. So if I have methanol, CH3OH, okay, and that's a liquid, and I put it in water, how many particles does it break up into? Trick question. How many particles does it break up into?
It's not aqueous.
It is aqueous. Yeah, but I'm putting it in water. Making it aqueous. How many no, just 1 particle. It doesn't break up in water. This is not ionic. This is not acidic. It's an alcohol. Alcohols don't break up. So it's just CH3OH liquid. How many? What's the Van Hoff factor? 1. All right. Let's move on and do a little practice problem. What do you say?
Of course.
Of course, he says. All right, good. So here's the question. If we have a 2 molal NaCl solution or sodium chloride solution, table salt solution, what will the freezing temperature be? All right. So the equation we're going to start with then is this one. Okay. So change in freezing temperature is equal to I times the Van Hoff factor, times the constant, the freezing point constant for water, times the molar concentration. I is the Van Hoff factor. Okay. And what is the Van Hoff factor for sodium chloride? 2. So I is 2. Now, the freezing point constant for water can be found in your test references, okay? This is an honors chemistry class, so your references will be the AP chemistry references, and you're looking for something down here in the lower right-hand corner on the first page. All right? Well, what does it say? Okay, it's right here. What's our constant?
1.86 Kelvin.
Okay.
Kilograms
1.86 Kelvin times kilograms over moles. It has moles with a -1. That means it's over moles. Okay. And then we've got a 2 molal solution. Now, what units of measurement make up molal? What units of measurement make up molal? Moles of what? What? Moles over kilogram. So moles over kilograms. Okay, so the light should be coming on here. What do we do next? Cancel. Kilograms cancel. Moles cancel. We're just left with Kelvin. What does Kelvin measure? Temperature. What are we trying to find? Temperature, or change in temperature. Okay. All right, so this comes out to be 7.44 Kelvin. All right, that's our change in temperature for freezing. Okay, now there's a problem with this. I'm sorry to tell you, there's a problem with this. And here's what you need to know about this. When you add a solute to a solvent, the freezing point temperature goes down. This is just the change in temperature. But which direction is it going? Down. Okay? So the actual change in temperature is a negative change.
Is that the same with like boiling temperature?
No.
Like it'll go up?
The boiling temperatures always go up. As you add solute to solvent, the boiling temperature over the pure solvent boiling temperature goes up. The boiling temperature of the solution increases. The freezing temperature of the solution decreases over the freezing temperature of the pure solvent. Okay?
So should this number be negative?
So really, when we use it in the next step, we'll need it negative. Okay? So here's what's happening. So delta TF is actually a negative 7.44 because it's going to go down. Kelvin. All right? And this is where we need that first equation we talked about. Okay? And so that change in temperature is equal to the final temperature, that's what we want to find, minus the initial temperature. So what is the initial temperature? Meaning, what is the freezing temperature of pure water without any solute in it?
32 degrees Fahrenheit.
She used the F word in a chemistry class?
Zero.
Really?
0 degrees.
Fahrenheit, she said. Yeah, it is 32 degrees Fahrenheit. I used the F word too. It's all right. We don't want to use that.
0 degrees Celsius.
0 degrees Celsius. Well, this is in Kelvin, though.
Converted.
So it would be 200
273.15 Kelvin, right? Good. All right. So, let's see. We got to isolate the unknown. Now, this is addition and subtraction here, not multiplication and division. Most of the math we've been doing so far has been multiplication and division. So, if we had multiplication, we divided to undo it. We had division, we multiplied to undo it. How do we undo addition and subtraction? Okay, the opposite. So, if it's subtracted here, I need to do what to undo it? Add it. So, I'm going to add 273.15 K to the right-hand side. But when I do it to the right-hand side, got to do it to the left. So, we're going to add 273.15 K to the left-hand side as well. And we get, well, this actually cancels out because this becomes 0. So we got temperature final. And we do the math over here. What do you get? Yeah, get that calculator out. Why not? How would you not get the calculator out? All right, so that's the new freezing temperature when salt is added to water in this concentration. Okay? All right. Here's the neat thing, though. You can do this too. The starting place for Kelvin temperatures and Celsius temperatures are different. Absolute 0 on the Kelvin scale is 0. Absolute 0 on the Celsius scale is negative 273.15. Right? But while they start in different places, the size, if you could call it that, the size of a degree C and the Kelvin are the same. Okay? So, the change in temperature is the same for Kelvin and degree C. Therefore, not the same temperature, the temperatures are different, but the change in temperatures is going to be the same on Kelvin or degree C. Therefore, the change in temperature for this solution, in the freezing temperature for this solution, on the Celsius scale, is 7.44 degrees C. Okay? All right? We're not saying that the temperatures are the same. We're saying the change in temperature is the same. So we could write this equation like this. We could say negative 7.44 degrees C equals temperature final minus what's temperature initial on the Celsius scale? 0. Okay? And so now we're going to add 0.00 degrees C over here and add 0.00 degrees C over here. And our temperature final is negative 7.44 degrees C. That makes sense? All right, let's check and make sure we did it right. Let's convert degrees C here on the scale, on the Celsius degree temperature scale, to Kelvin. Can you do that? What do you got to do to convert Celsius temperatures to Kelvin temperatures? Add 273.15, which is what we did right here, isn't it? It does come out the same, doesn't it? Huh? Well, if the question doesn't specify which unit of temperature to use, you can use either Kelvin or Celsius. But if it specifies, you got to use the one it says to use. Okay? So you can find the Kelvin temperature and convert to Celsius. You can find the Celsius temperature and convert to Kelvin, or you can do the two math problems separately. You with me? All right then. Let's find the boiling temperature of this solution. Let's find the boiling temperature of this solution. Okay? So we have a 2 molar solution of NaCl. So now we have a change in temperature for boiling. Okay, that's what delta T sub B means. And the Hoff factor times the constant for boiling times the molar concentration. Oh, hey, same equation, just different subscripts indicating a different constant here. Okay? All right, what's I? 2. If the solute doesn't change, I doesn't change, okay? The solute is still sodium chloride. But what is the boiling point constant for pure water? 0.512 Kelvin times kilograms over moles. And what's the mole concentration? 2.00 moles per kilogram. We can cancel out units and do the math. Okay. So let's do 2.048 Kelvin. But how many significant digits do I need here? 3. This has 3 digits. That leading 0 is not significant. This has 3 significant digits. And this is a counting number because we counted the number of particles, right? So it's infinitely significant. We ignore this one. So we need 3 significant digits. 2.05 Kelvin is the change in boiling temperature. Boiling temperatures increase or decrease when you add solute to solvent? Increase. So this is going to stay a positive number. We're going to plug it into this equation. Delta T sub B equals temperature final minus temperature initial. Okay. So delta T sub B is going to be 2.05 Kelvin. Temperature final minus temperature initial. What's the initial temperature of boiling for water? 100 degrees C. What is it in Kelvin?
No, that's it. That's its freezing.
You add 273.15 to the 100.
That'd be 373.
373.15 Kelvin. Okay? And so you do the same math where you add 373.15 Kelvin to both sides. Okay, and that's going to cancel out, so we've got temperature final over here. And this becomes 375.1020 Kelvin, right? That's the new boiling temperature when you add salt to water to a concentration of 2 molar. Okay? What is it in degrees C? Well, let's see. 2.05. How many degrees C is that supposed to be, the change in temperature? Same. Degrees C equals temperature final minus, and what is the boiling temperature of pure water on the Celsius scale? 100 degrees C. Add 100 degrees C to both sides.
102.05 Celsius.
All right. Either one of those is acceptable for the answer as it was stated.